All right, so hopefully you've had a minute to trigger your memory on some of these. We will be discussing most of these throughout the lecture. I just want to talk about a couple of them first. With KSP, we are dealing with what types of scenarios, like what type of equilibrium is this? Say it again. Say again. Okay, so we deal with salts a lot though. So what types, like what phase? So generally insoluble salts, right? Things that we would classify as insoluble. A lot of lead, a lot of mercury, a lot of silver, a lot of so nitrates are really not a big deal because they're all soluble. Acetates are mostly all soluble. Group 1 metals are all soluble. So we won't be dealing with things like that. We'll be dealing with things we've always called precipitates. But are they truly all precipitating? No. So we've been lying to you the whole time just so you could get through honors chem to learn this now, right? So the idea is that there's a little smidgen of ions that are coming off of the solid, and that smidgen is going to be the part that we look at to say, hey, how soluble is this species? So these values here are all going to be what? Hold on. So that's less than 3 grams per 100 milliliters, yes, but all very, 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 very small. Okay, because they're still mostly precipitated, but just a hair of ions are coming on. So there's still very few products, meaning ions, in the grand scheme of things. So these are all very small values. So you should always expect KSP values to be very small. So comparatively, barium sulfate and so on. Who is the least soluble? Cadmium sulfides to the negative 27th, right? And why can I compare these specifically? Why am I allowed to compare? Like, I'm letting you compare these using their KSP values. There's a reason why. No, these are the reactants. These are the solids that are being dissociated. They have the same ion ratio. We cannot compare anything unless they have the same ion ratio, because as you look at them now, how many ions are each of these producing in solution? 2, barium, sulfate, cadmium, oxalate, cadmium, sulfide, and calcium and carbon. So if I had like lead 2 chloride and I compared it, I wouldn't really be able to compare KSP values because a different number of ions means the KSP is going to be calculated differently, and I can't compare them because they're not calculated in the same manner. So that's why 2 and 3 kind of went together, because it's called relative solubility. You must have the same ion ratio to compare those. Otherwise, you have to calculate, right? So we're going to calculate those shortly. Solubility can change with what? Temperature, good. When does Q not equal KSP? When it's unsaturated and when it's supersaturated. And then what role, let me go down here first, what role does pH play in KSP? Anybody? JT?
I don't know if this is right, but I feel like
so not quite. It's actually going to be opposite of what you just said, but the idea is that bases make bases less soluble, because we're talking about ions, and if you already have a lot of that same ion, Le Chatelier's principle comes into play, and it's not going to push to make more of the same ion, so we already have a lot of it. So that's something that we're going to talk about at the end. This is something that's kind of new to us, as is the common ion effect. We did speak of this briefly on like the second day of equilibrium, but these are 2 pieces that are big players in KSP. Okay, yeah, let's skip the rest of this for a minute. All right, so we're going to talk, you guys can write down what you need to. I'm going to make sure we're on time, so I want to make sure we're doing some practice in class today. I'm going to periodically be working through some questions on the KSP and MSI. So if you printed it, I'm going to be working through like some examples of it. You didn't find no big deal, I'm going to have it up here as well. So if you want to keep that out on your desk, then you can you see past this chair? It's kind of high. So when we're talking about KSP, the scenario is a solid that's been dissociated, and the ions that are coming off, like for example, silver ion and chloride ion, are aqueous, but the solid is solid, right? So when we're talking about equilibrium, which of these things actually matters? Say again? Aqueous only, right? Solids don't matter. So we're going to be we have a very particular look to a KSP expression. It looks very different than everything else we've dealt with. So the word dissolution or dissociation are 2 terms that you'll see alongside of anything KSP related, because we're talking about the solid dissociated and the solid going through dissolution, which means to go into solution. as your solid, for example, the silver chloride, undergoes dissolution or dissociation, we're increasing the concentration of ions to a point. So what is that point that we're going to increase the ion concentration to? Equilibrium, which then we would also say is a what type of solution? Saturated solution. So it's not going to just infinitely keep ionizing, or dissociating. There's a stopping point. But does it just halt and stop kind of moving? No. What's the word that means there's back and forth? Dynamic equilibrium, right? So there's a fluctuation between ions dissociating and ions precipitating. There's this constant back and forth that we call equilibrium, which is the state of a saturated solution. So hopefully you were reading, listening, and writing on what you need to, not copying this, because you can print this off on the website if that's what you want to do, okay? So as we get to the saturation point, we know there's dynamic equilibrium at play. We will see, we won't see this, but we know the ions are recolliding with each other and reprecipitating, and then the precipitate is redissociating, and then the ions are colliding and reprecipitating, and this is constant back and forth. So we can still continue to talk about rate forward and rate reverse, except we might call it the dissociation versus the precipitation, but we still mean rate forward versus rate reverse. Thumbs up if this makes sense? Conceptually? Okay. So, as a dynamic equilibrium begins to occur, but that's what we've just stated already, that we're going to meet saturation, and that's when we are holding a specific amount of ions at a given temperature. So we will make sure that this is temperature dependent. Just like all equilibria are temperature dependent. So if the saturation point is temperature dependent, saturation gives us a certain number of ions in that solution. What is also temperature dependent? We put those ion concentrations into something to calculate the Ksp expression, right? So if the saturation points, meaning the concentration of ions, is temperature dependent, remembering that we plug those ion concentrations in to find Ksp, it means Ksp is also temperature dependent, but we kind of already knew that because all Ks, Kcs, Kps, Kas, Kbs, Ksps, they're all temperature dependent. They depend on how far we're going to the left or the right, or specifically for this one, how it's affecting solubility. So, as we kind of just went over in warm-up, the Ksp is referencing the saturated solution. So what we do have to compare, given non-saturated solutions, we have to compare the Q to the Ksp to determine if it's above or below saturation, meaning supersaturated or unsaturated. What was Q called back when we were like Kc and Kp? It had a name. Its symbol was Q, but it was called something. Reaction quotient. It's just called a reaction quotient. It's just what it is. But when you're talking about Ksp relationships to Q, we don't call it reaction quotient. We call it an ion product constant or an ion product. And so it's the same calculations, the same setup as Ksp. It's the same theory. You do a lot of comparisons between Q and K. It's just called something different. So just be familiar with like the terminology. So if it's ever asking you to find the ion product constant, you know, like what is that? It means find Q, and then you're good to go from there. So if I give you initial concentrations like, we add 0.1 molar silver nitrate and 0.2 molar sodium chloride, These are giving me initial concentrations, and we're going to cause a precipitate occurrence, silver chloride, through like a double replacement reaction. But we would be given those concentrations, and we would plug those into Q. But we're gonna do this in another example later. Okay. Thumbs up if conceptually we're good here. Okay, so it's the scenario of solubility. Solids make ions. I can make more ions at higher temperatures generally. And once I get to the saturated point, I plug those concentrations into KSP. I look at KSP and I'm like, oh, that's pretty small, right? So not a lot is going to be dissolving. Okay, and then this was the relative consideration of solubility that we just spoke of earlier. But essentially, if you have a large KSP, just like in any situation we've spoken of so far, let me write this example back out. In any situation we've had so far, a large value for K means what about this reaction? Right, it's favoring the products. We're favoring the production in the forward direction to make these products. So if you have a large K value, it means that your salt is more soluble because we're having more ions dissociate. Does that make sense? Yes? Okay, because this is a very, very specific scenario. It's talking about solids going to ions. Because we're going to have more product over no reactant, because we will not put the solid into the KSP expression. But we do a relative comparison only when you have the same number of ions. And that's the only valid time to ever compare KSPs to say who is more or less soluble. So when we start to talk about molar solubility, we know what molarity is. So molar solubility is related to that. So if you ever hear molar, still kind of consider molarity. And this is in solution. These are all aqueous solutions. So that is a liquid or aqueous liter. If they ever ask for just generally solubility, many times they'll give you the units. But if they don't, go with these units. Go with grams per liter. Because in everyday world, we're not talking about moles. We're talking about grams. We're like, hey, 10 grams of this dissolves in 100 grams of water, or 100 mils of water, or 0.1 liters of water. So we're not always looking at moles in everyday life. Questions so far, guys? Are you okay? Okay. So write the KSP expression for that example on the board. Make sure you know what you're doing here. Yeah, for the silver chloride. Biggest mistakes that people make for this scenario is they forget to put the ion charges. And if you don't put the ion charges, you're not technically talking about ions, so you're not technically talking about solubility, so you would not get your credit. So just be very cognizant of that. Most of you guys do okay, and I try to make sure I lead you in the right direction with this. We're not going to put that over anything. So it's not over silver chloride, it's not over 1, it's just this. So that's why these look very peculiar. Yeah. Not for a KSP. It's for anything, and that's what I'm really trying to clear up for us. We don't just start with a solid, right? We generally form solids through double replacement reactions where we make precipitates. Like we've done that, I don't know, for a year of our life now. We know we make that through double replacements, but we will never, ever, 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 ever write a KSP with reference to the double replacement, because that's not what KSP stands for. It means solubility product. It means from this solid, what are my products and how soluble are they? We only ever write KSPs for this style of reaction. So make that very clear. And I emphasize that because people still mix it up. They want to put KSPs for all kinds of other reactions, but it's only for this. Okay. Okay. So before I move on, what is this? Solubility curve, right? On the line represents what types of solutions? Huh? Saturated, right? Saturated is on the line. Above the line, if you have like some amount of grams that's above the solubility, it's going to be super saturated. And if you have any number of grams that are below the solubility, it's going to be unsaturated. So if you ever have to read a graph, which is very unlikely, that's, well, I won't say it's unlikely. it's very easy, but it's unlikely to grab information from that for a problem like this. Okay, so this is number 1 on the NMSI. And forgive me, I have calculated a lot of these. I've calculated all of these. But I want to make sure I'm slowing down so that you can practice calculating too, because your muscle memory will kind of trigger when you have to do this on your own too. So can you calculate this out? Alright, so I'm going to show you a couple, and then I'm going to stop and let you practice on your own. Once we get the hang of it, I'm going to try to do a couple different styles of problems so you're familiar with them. And then we'll see where we are, and you guys can let me know if I need to do more. Okay, so we have copper 1 bromide, and it's measured to have a solubility of 2.0 times 10 to the negative 4th molar at 25 degrees Celsius. Calculate its Ksp value. So one thing I did not mention to you is when we had the word molar solubility up there. Molar solubility is X. Remember, like when we do ice boxes, like we have to find X? Molar solubility is X in basically every scenario. So if we're ever like given, for example, the molar solubility, it is X. So we first need to start off with writing out the dissociation equation. Okay, so what am I writing first? Cu, Br, right? So copper 1 bromide, solid, equilibrates to Cu 1 plus and Br 1 minus, aqueous. No matter if it asks for you to do that or not, you should do it because it's going to verify that you're clear in your numbers that you need to be adding in here. So after we write the dissociation equation, we need to determine if we need to do it like a true icebox. Do we know X? Things like that. So we certainly know X because we know the solubility of this. So if we have a solid, we don't really care how much we have of it because it's irrelevant to our equilibrium. But assuming we have some number here, which we don't care about, and we have 0 and 0 of both of the ions pre-dissociation, I'm going to add a certain amount to each of these. How much do I add? Like, assuming that we're going to do a little icebox here. How much am I adding to copper 1? Okay, I know that, right? So, but I know it's X, right? So I'm adding 1X amount to here, and I'm adding how much here? 1X. But I know what X is, so I'm able to just go ahead and say, hey, this is molar solubility. As this dissolves in a 1-to-1-to-1 ratio, this is how much copper 1 is forming, and this is how much bromide is forming. So 2.0 times 10 to the negative 4th molar, 2.0 times 10 to the negative 4th molar. I'm good to go now. Before I start plugging in, we've written out the dissociation, we've written out the ice. We need to write out the Ksp expression first. So what's that Ksp expression? Cu 1 plus times Br 1 minus. So then what are we plugging in here? 2.04 or 2.0 times 10 to the negative 4th molar squared because it's X times X, which is X squared. You guys could likely do that in your head, but I'm ready when you are. All right, so 2 times 2 is 4. And then anytime you multiply an exponent, what do you do to the exponents? Add them, so 10 to the negative 4th times 10 to the negative 4th is 10 to the negative 8. And is there a unit on Ksp? No. What's that, Emily? I'm solving for K because this doesn't very clearly show you it's a saturated solution, but it says its measured solubility is that, meaning like that is how much it dissolves in that liter at 25 degrees Celsius. So this is trying to tell you it's a saturated solution. So hence, if it's a saturated solution, we're solving for Ksp. Yeah, I'm sorry, use the equilibrium values for K because it's the equilibrium constant. Good. Okay, so let's move on from there. Are we okay on this one? If it says solubility or molar solubility, that is X. All right, so next one, I want you guys to start without me. We'll do the same process. We doing okay? I did 2 squared times 3. I just tried to calculate my head. I put one on my paper. 4 times 27. Thanks. So that shouldn't be changed too much. All right, so in the method I selected to use, instead of writing out that x value 1.0 times 10 negative 15 3 or 4 times, I saved it to the end because, you know, Butterfingers over here, we fixed it now. But in reference to starting off, try to set up like it's a mini icebox, but what you're seeing is every single time you have you have 0 initial products, so you're just adding a certain number of x's or the molar solubility they gave you. So I chose to use x, so I had 2x and 3x respectively. So when you're plugging them into your expression, bismuth 3 plus squared times sulfide to the 3rd power, 2x squared and 3x cubed is then going to give you 108, and then you have 108, x to the 5th. I think this is simpler to simplify and kind of collect it together and then plug in x, which is your molar solubility, but you should get a very, very, very small k value. Are we okay here? If you did not do it this way, you would have then had 2 times x amount, 3 times x amount, and plug those values in here and here. So it would have worked out exactly the same way. Okay? All right, so I want you guys to start this one first. I think you're smart cookies, and then I'll jump in. Okay? So read your copper 2 iodate. It tells you the Ksp value. I want you to try to find the molar solubility. Can you just tell me in one word exactly what you're solving for? Can you tell me? So you're solving for solubility, but what is that really to us mathematically? It's x. I want you to solve for x. That's what that means. That's what equation you're interpreting. All right, so in reference to how we would approach this is, since we know we're looking for solubility, it means molar solubility. You need to solve for x. We don't know any of the x's. So if this is going to equilibrium, we have a certain amount of solid, which nobody cares about, that's going to dissociate to making a 1-to-2 ratio of x amount of ions. So who assigned x and 2x for our ions here? Okay, so we should like either underneath our equation write it like this, or be very clear on how you're plugging it in with your KSP expression written out also. So in reference to this, do make sure you're putting 2x parentheses squared. That is also a common mistake I continue to see mathematically, because 2x squared is different than 2x parentheses squared. So 2 squared is 4, x squared times 1x is going to be x cubed. Then you're dividing by 4, and then what are you doing? Cube rooting. You can either cube root in your calculator or raise everything to the 1/3 power, and that's the same as cube rooting, and we should get approximately this. 2 sig figs though, so round this to what? 3.3 times 10 to the negative third molar. So that would be our amount of copper made. And what if I asked for the concentration of iodate at equilibrium? It would be what? You would times it by 2, right? It's just double that. So copper is related to iodate in a 1-to-2 ratio. So that's the amount of copper solubilized at that temperature, and then double that would be the amount of iodate dissolved. Okay. Okay. Do we need to do this one in low? No, we're good. All right. Let's move on. All right. So now we're going to talk about the relationship between Q and K. So we write reaction quotient for what's the other one? Ion product constant. So a lot of times they tend to be interchanged with using QI. A lot of times the ion one, which is our KSP comparison. So take a minute and write this down. No. Well, more of it's not at equilibrium. Yes, but there's a higher rate going in the reverse direction to precipitate. Yeah. We can't stop the flow of it all the time, so we just have one going faster than the other. So back in the day, like last week, when we were talking about Q versus K, we said, hey, like, why would I do this? What would the question say to prove me you compare Q to K? What was that question? But is that how the question's phrased? Hey, figure out which shift is going to occur. How's it going to proceed? What is it? What did it say to prompt you to do that last time? All right, so one, you could see all the initial concentrations. So this is like Q versus K thoughts. So you'll be given all initial concentrations, and your job is to figure out proceed left or right. What's another phrasing or way the question would be phrased to tell you that? They would give you the K equilibrium values so you could compare. It would also say, is this reaction at equilibrium? It's as simple as that. So they would give you the initials, and then they would say, is the reaction at equilibrium? Well, if it's lower than K or greater than K, then we would say, no, it's not, and then we would need to proceed from there to get it to equilibrium, and we need to subtract one side, add to the other. So with a KSP example, it's not going to say, is it at equilibrium? It could say, is this a saturated solution? Okay, because a saturated solution is at equilibrium. Or it could say, will it precipitate form? Because we all know that this is the general format for any KSP, solid yields to ions. So what it's basically saying is, will it shift left? Will it reverse the reaction? But we would never know that until we knew the KSP value compared to the Q value, and then we would know, are we going to proceed left or right? So will of precipitate form should trigger you to compare Q and KSP. So we would be given initial concentrations essentially. If the Q is too low, that means we have too few or too many ions. Too few ions, because remember, Q is set up the same way. It's ions over nothing, no solid. So over nothing. So the Q value is too small, we just don't have enough. So we need to continue to push right to make that unsaturated solution saturated, right? It's going to stop it saturated. If the Q is too large, then what? Too many ions. And if we have too many ions, it's going to reverse the direction and it's going to precipitate out because it's unstable and it cannot maintain that ion concentration at those conditions. And then we know that the Q will eventually meet the KSP. That's going to be the saturation point. It's not going to go farther than K. And that's kind of the main point we made on the last time too. We don't push past K. We make Q equal K eventually. Thumbs up? Okay. So we kind of talked about this already. Move on. So this such situation actually gives you two full reactants, like as if it were a double replacement reaction. We do not write the double replacement reaction out because I do not want you to attempt to use that as the KSP expression. But we know that's how we make precipitates, right? We do a double replacement. So this is your thought process. Anytime you're given a mixture like reactant 1 and reactant 2, you're first going to make their previously given concentrations, what they would be once they're mixed together. Because once you mix two different volumes together, what happens to your concentration? It decreases, right? It's diluted because it's moles over liters, so we're dividing by a larger volume. So we have to get our diluted initial concentrations. Once we get the initial concentrations, the true ones, we'll find Q, compare that to K, and then we'll decide, is it going to precipitate more, or make more ions, or am I at equilibrium? That's the point when we'll compare Q and K. So let's do the first step first. A solution is prepared by adding 750 mils of 4.0 times 10 to the negative third molar cesium-3 nitrate to 300 mils of 2.0 times 10 to the negative 2 molar potassium iodate. Will cesium-3 iodate precipitate? And there's a KSP value. A lot of information, right? But what we have here are two pieces for each initial reactant. And I need to take their current concentrations and dilute them. What comes to mind? Essentially the dilution equation, but we're not going to run N1 V1 equals N2 V2. We're going to kind of modify that. So we're going to do, so if this is what you're thinking of, right? What are you essentially solving for to get the new concentration? Probably M2. So you're just going to multiply molarity times volume. Well, what does molarity times volume always get us? Moles or millimoles, right? It doesn't matter as long as we're dividing by the appropriate second volume. So I can do milliliters times molarity, and I can get millimoles. And then I'll divide by V2, which is going to be not this second solution. It's going to be the total, right? 750 plus 300. And that's going to be my new concentration. So I'm going to do kind of this for both of these reactants. Okay, but I don't really care about the nitrate. I don't really care about the potassium. Specifically, I care about the two ions that are creating this precipitate. So I care about Ce3 plus and IO3 1 minus. Okay, so let's do that. So 750 milliliters times 4.0 times 10 to the negative third molar divided by what? It's kind of hard to see, so I was trying to get you guys to write down the pieces. Dividing by what? 1050, right? So it's a little over a liter. And this is total volume. That's going to give us the concentration of one of the ions we care about. Not the whole, not cesium, that was cerium. Where's cerium at? Yeah, it would be, where do you see it? Oh, thank you. That was cerium. Okay. So that's cerium 3 plus. And then what's that concentration, guys, when you get there? Remember, the milliliters cancel each other out, so we're still stuck in molarity. To what? 857 times 10 to the negative third molar. Okay, so this is one piece of the puzzle we need. That's the new initial concentration. So do the same thing. What am I doing for iodate? 300 mils times, so its concentration here, good, so 2.00 times 10 to the negative 2 molar divided by what? The total, again, 1050 milliliters total, and that's going to give us iodate, which is 7.1. I'm going to put 4 just to continue. These are not final answers, so it's cool. We're over 6 days right now. And this is, okay, this is iodate. Okay, so we have 2 ion concentrations initial now. You guys determine if it's going to precipitate. A lot of us writing association equations out. Be aware, you're going to forget the coefficients if you don't write the equation out and then the expression. I do it just to save you from yourselves. So what's the dissociation equation? C, huh? Solid dissociates to. Good, 3 iodates. Please don't forget the coefficient there because it would be problematic finding the Q value or the KSP. So then your Q/KSP is cerium 3 plus times iodate 1 minus Q. Good. So the coefficient is important. So then we plug them in. It's a little tedious, but you know, it's chemistry. When you get there, just shout out the Q value for me. 5.3 times 10 to the negative 10. Can I get a yes on that? Good? Okay. So Q, 5.33 times 10 to the negative 10th. How does this compare to the KSP of 1.9 times 10 to the negative 10th? Say again? All right, raise your hand if you say it's greater. All right, you have participated in my survey. Raise your hand if you say it's smaller. All right, let's try it again. Bigger. I'm sorry, is Q greater or lesser than K? Okay, it's greater. So they're both 10 to the negative 10th, so we're good here. We're just comparing this number to this number. 5.33 is greater than 1.9. So it is more or less, sorry, are there too many or too few ions? Too many. Okay, so this is greater than KSP. So then, and this is just our thought process. You don't have to write this for yourself, but too many ions means it's supersaturated, so it will precipitate. Good. The way we would justify that is just to say, mathematically, Q has been calculated to be greater than K, thus precipitation will occur. Point blank. No need to explain anymore. Just leave it like that. You doing okay? I'm going to hold off on exercise 6 for a minute, okay? I want to make sure we're clear on how to do some basic stuff first. Can I go forward? Do we have our little process written down from purple up here? All right, sometimes you need a process to refer to. All right, so we have briefly talked about the common ion effect. This is an equilibrium of calcium. What's calcium carbonate, by the way? Where's that from in everyday life? chalk. What else? That's something fossil. So seashells are made of calcium carbonate. So what they do is they can make this artificially or synthetically in the lab, but they used to take seashells and grind them up, little lithopods, and that's what they would make helms, like rolades, helms, chalk, anything else carbonate. That's about all I know right now. Because that's where they got it. It's easy to get in some regions of the world. Fun fact of the day. All right, so we have calcium. Let's pretend this is aqueous calcium chloride. If I add that to solution, what will happen? Which way will this shift equilibrium? Louder and prouder. To the left. Good, because essentially, what does this mean we've added? Separately, what have we added? Calcium 2 plus and Cl minus. There's two of them, but it's still Cl minus. So what we look for is this an equilibrium? Yes. Is this an equilibrium? No. So nobody cares about that. We care about calcium itself. So we've essentially added a product, and if we add a product, which way does it shift? Left. Okay. So now that we know we're talking about solubility, if I shift left, what have I done to the solubility of calcium carbonate in this solution? I've what? I've decreased the solution. Decreased the solubility. Because I have not allowed as much calcium and carbonate to dissociate by way of shifting left. Questions?
So if you get compounds, so it's not English,
Are you talking about this one?
yeah.
Yes. So his question was, if you get calcium chloride and you're like, well, I don't see that specifically in the BCE, if I don't see that specifically, then I needed to consider like the common ion effect, meaning I need to ionize them to see specifically if the two ions are relevant, and one of them is. So yes, you do need to consider ions, especially for soluble, like aqueous situations, because we're all talking about in aqueous. So essentially, can you give me the common ion effect in a nutshell? Less than a sentence. Raise your hand if you're good. Go for it, JT.
Basically, what the common ion differentiates into supplies the reactant hydrogen.
Okay. So in the case, I'm gonna just limit that to one of the phrases you said. In the case of all of our solubility expressions, it's always solid yields to ions, right? So if I have a common ion, it's always going to shift which way? Because those are the ions, and if you increase them, they're going to shift left. But, oh, actually, no, I will justify. We'll talk about how common ion effect works in just a second, too. So, common ion, or an ion that impacts a species in equilibrium can change solubility. Because you're right, we can essentially increase the solubility in some situations, especially with acids and bases. All right, so looking at this example, what's the molar solubility of iron 2 hydroxide in a solution of 0.05 molar sodium hydroxide? Okay, we're looking at what true equilibrium here. What's the equation? Say again? Not sodium hydroxide, because that's not the thing that is, and we know that because sodium is a group 1A metal. It's not the solid here. It's this just like, hey, I'm in this solution. I'm a part of the aqueous solution. So who's the thing we look at? So iron 2, and it kind of tells it to you because it says what's the molar solubility of iron 2 hydroxide. So this is the Ksp guy, that one. So we have to go ahead and dissociate, right? All right, into what? Fe2 plus. Can I do, just for my own sake, I found the Ksp of iron 3 like a dummy, so we're going to do iron 3 just for now. All right, go ahead. 3 OHs, thank you. I just looked this up earlier and I must have looked at the wrong one. So, all right, so continue. What do I know is initially present? Okay, but I don't really care about the sodium, right? I care about the hydroxide. So this is the common ion, right? So if we have a common ion, that means we initially have that present. So ice up, right? So we have our ice box. Nobody cares. So just kind of scratch out that side. How much hydroxide do I have initially present? 0.05 molar. Okay. So as this dissociates, because you notice we're not giving anything about iron, so we assume what's here? Zero. So as this dissociates, what am I making of iron? Iron 3. You don't know, right? So what do we call it? X. Whew. Okay, what am I making of OH? 3x, right? Okay, so we're going to get into now X at equilibrium, 0.05 plus 3x. And the Ksp for iron 3 hydroxide is 2.5 times 10 to the negative 39. Okay, so we have this information right here. What else do I need to go ahead and set up? The Ksp expression, good, okay. So Ksp is equal to what? Iron 3 times hydroxide to the third, okay. What am I plugging in for iron? X. What am I plugging in for hydroxide? So we want to put this whole thing, right? We know that's going to be like cube root something. Ain't nobody got time for that. What are we probably going to do for this? Neglect that. And how do we know we possibly can neglect X? This is so small. Am I making very many? No, to the negative 39, people. We're not making barely any ions. So this is probably out, which makes my OH value actually what? The value that we had initially. So we're saying that initial hydroxide concentration is not changing very much. We're going to consider at the end if we were truly able to do this, but we are. Okay, but it's still cubed. And then this was what? 2.5 times 10 to the negative 39. Please solve for X. When you're ready. 2.0 times 10 to the negative 35. How did I get 38? Butterfingers? Most of you guys said 35? Okay, I believe you. And this is the molar solubility. Okay, how do I verify I was good at neglect X? Take this and divide it by what? 0.05 times 100, and was I able to neglect X? Way less than 5%. Like, I don't even have to do this calculation. Yeah, it's to the negative 35th, people, right? It's a teeny tiny number. And, oh, I didn't conclude with this. So, in essence, and we didn't calculate this prior to the common ion effect, but make a conclusion. Do you think that there's more, iron 3 hydroxide had a higher molar solubility in this situation, or in a situation where there was no sodium hydroxide present? Talk to the person next to you. Which one do you think has greater solubility? All right, come back to me. Raise your hand if you say this situation here has greater molar solubility. All right, raise your hand if you say the non-sodium hydroxide presence has a greater molar solubility. All right, since you all didn't raise your hand the first time, you all have to raise your hand the second time. You must participate in my surveys. So Christian hesitantly, yes, this is not as soluble because we've essentially included this hydroxide ion, right? And what have we done to its equilibrium by the nature of including this? We've shifted it left, right? We've made more precipitate form, less ions form, so we've decreased the solubility by the inclusion of a common group. Good. Okay. We just did that. Okay. So talk to each other for a moment. You've got like 30 seconds why this is true. What background principle can you apply? All right, I just heard 3 people say it. Le Chatelier's principle, wonderful. Okay. So we know Le Chatelier's principle is behind all of this because by the inclusion of a certain product or reactant, then it's going to cause shifting because really because Q is greater or less than K. So once we know that we have a higher or lower Q value, then we're going to cause a shift or to proceed left or right. So this is the last part really that we haven't talked about yet, and it's pH. So if we have a solution that is affected by the inclusion of an acid or a base, we can shift its solubility. Magnesium hydroxide is a pseudo-soluble, slightly soluble compound, and it will dissolve or dissociate into magnesium 2+ and 2 hydroxides. So answer this question with the person next to you. How would magnesium hydroxide, its solubility, be affected by the inclusion of OH, meaning a base, and H+, meaning an acid? Come talk to somebody. Come on. These lovely people here wanting your attention. All right, come back to me, okay? So, William, what do you think is going to happen when I add hydroxide to this equilibrium? Okay, and what happens to solubility? Good, okay, so adding OH increases OH concentration, which is a product, which will cause a shift left, and then precipitation will occur because we've gone towards the solid side. So a base and a base is more or less soluble. Less soluble, there's more common ion. That's a very obvious case. So how about the inclusion of H+, Chase? What you think? Acids, including an acid here in this equilibrium. So you're questioning yourself. It has to be the right answer, right? So we're kind of dealing with opposite things. But can you explain it? That's the part for this one I want to make sure we're clear on. Give me a shot here. What does H+ react with? Okay. All right, so everybody, what happens to OH now? Okay, well, it turns into water. So what happens in this equilibrium to OH? Hold on. Give me baby steps. It decreases. Thank you. Decreases its concentration. Okay, so once we've reacted H+ with OH-, we've made water. It's decreased the hydroxide concentration in solution. Then it will shift right and more ions form, right? Which means to increase solubility. That one's more challenging because you do have to think about the micro reactions happening kind of alongside of this. It's not truly a common ion, but like JT said earlier, it can change solubility. We don't say it only decreases. It could increase solubility by the nature of how this secondary reaction is occurring. Okay, so just a heads up, I'm gonna have a couple more practice problems for you guys specifically, but I want you guys to work on an FRQ first, which is on the back that I just gave you of multiple choice. So the very last page, it has like 2001, right? 2001 FRQ. Okay, work on that. You can work with the person next to you, it's fine, chat, but I'm gonna say I want your attention back in like 8 minutes. I want to see where you are at that point. And I did print out some KSP multiple choice, but I'm only asking you to do like 10 of them. I'll take those out further, okay? So how about that FRQ? Please not try squeezing on that little sheet of paper. Do you need paper? I got some.
You good? You stuck again?
I'll look over your shoulder. Where you
Yeah.
up here? Okay. had it calculated wrong, but did anyone else get? Hold on, before we move on, double check my work. Is my calculations majority rules? Double check yours. Usually I have to double check myself, but you guys can double check for me. Yeah, I think it's 2 6 weeks. Yeah, please. Okay. I'm going to leave this up here for part B. This is the dilution of initial concentrations. You compare Q to K. I'm going to put that in for you. And then we'll wrap this up in less than a minute here. in your PB in this reaction. You'll have an initial amount there, an I of ice.
We did some of these in for your study purposes.
Alright, so finish where you are in 10, 9, 8, not going to count down from here. Finish where you are. Alright, can I take this off the board? Okay, so I made it through B with you. If you made it farther, we'll chat some more tomorrow. Open up the KSP multiple choice, which is going to be like maybe a page back. I want you guys to do, what I've done is, KSP can go on forever. We can keep practicing, but some of you guys are going to be able to apply the same concepts to any problem I can throw at you. So I did one FRQ to say, like, this is pretty cumulative. If you can do that, you can probably do the rest. But I'm leaving you with optional textbook homework if you want. These are the practice multiple choice I want you to do for KSP. So if you want to highlight them or circle them on there now, do notice it says KSP at the top of the multiple choice. So I'm looking on which way for a second. The first pages, 1, 2, 3, that's what I gave you yesterday on mine. I know you started on paper, but I thought it would be helpful to have that in front of you. But on the back of the second page, it says practice, F2, solubility, equilibrium, KSP, and more. Those are the ones you're doing 1 through 9, 13, 16, 18, 19, 23, 27, 32. So make sure you circle those. Alright, is everybody clear on what I'm looking for here? You found the right multiple choice. One second. So you guys have your multiple choice from yesterday, 1 through 37, 32, 37. Okay. So we did like half-ish in intervention. If you did not, I do want to check that with you tomorrow. You know, give me a minute or less per question. You'll be checking those and these. So I specifically want multiple choice on my part. I have more FRQs on my website for KSP if you want to come to more KSP FRQs. But we are doing a KSP titration lab tomorrow. It's called calcium hydroxide titration lab. It's in your first packet I gave you. And I copied it so it's like 4 to a page. And you can cut it out and put it in your lab notebook. So please do not rewrite the background and the purpose and the procedure. Highlight it or something in that procedure so your lab notebook is prepped for tomorrow. Okay? So specifically do tomorrow. Multiple choice, make sure your lab notebook is savvy enough to go ahead and continue so that you're not prepping all that during the lab tomorrow. Bye, guys.